My name is Ben, and I'm the Chem 350 SI instructor, and today we're going to be discussing E1 dehydration mechanisms and the alkyl shifts that we can get with an E1 mechanism. Okay, so I'm going to run through an example of an E1 dehydration reaction, and this is going to be about as complicated as you can get, and you'll see why in just a minute. But notice that we have a secondary alcohol, and so that can go by E1 or E2. But if it can go by E1, you have to notice that you're going to get the same products, but you may also get some extra products with shifting of hydrides or of the alkyl group. So let's just look at what we've got here. We're always going to have the same first step, and that first step, whether it's an E1 or E2 or SN1 or SN2, is going to be the protonation of the alcohol with some acid. In this case, we have a sulfuric acid. So let's go ahead and draw the first step, and then we'll talk about why we can do E1 and what the consequences of that are. So that's the first step for E1. We're just making the alcohol a good leaving group by protonating it. So let's draw out what we get from that. We've got our O. It's got one lone pair and two hydrogens and a positive charge because it just gained a proton. So now we've got water that's a good leaving group, and we know that it can just fall off on its own. That's going to be our rate determining step. It can just fall off on its own. So let's go ahead and draw that. The reason it can fall off is it's secondary. It's not going to happen a whole lot, but it will happen, and so it's going to lead to some interesting consequences, and we'll talk about those in just a second. But let's go ahead and draw the carbocation that's formed from the leaving of the water. We've got just H2O floating around somewhere. Okay, so now we've got this is our alpha carbon, where our leaving group left, and it's our carbocation, and now we look for beta hydrogens. And beta hydrogens are on carbons that are one away from our alpha carbon. This is our alpha carbon. This is our beta carbon. That's also a beta carbon. And notice we don't have any hydrogens. These are methyl groups, and so the beta carbon on this side does not actually have any hydrogens to pull off, but this one does. So we'll go ahead and draw that. I'll redraw the water up here, and you can use water as the base because it has a lone pair of electrons to pull off one of these protons. So let's go ahead and draw that step where we take the water attacking the proton, and then those electrons falling in to form the double bond. And so we've got actually two products from this, and let's look at what those are. We'll go ahead and write out all of our products from this reaction. Products. So one of our products, if we draw it the same way and just put the double bond in there, is going to be this. Okay, and that is let's look at the stereochemistry of it. That is an E form of the alkene. But remember, when you do a dehydration, you can also get some of the Z. Now that's going to be less likely because it's less stable. But you also get some of the Z form, where you've got both of the priority groups on the same side. In this case, it's also the same as cis. So that's something you can get once you formed your carbocation and from an E1 reaction. These would also be products of the E2. But now here's where it gets tricky. Let's go ahead and draw another pathway and redraw the carbocation with our methyl groups. And remember, I said there were no hydrogens on this beta carbon. Well, you've got to look at what we've got here. This is where it gets a little tricky. Here we have a secondary carbocation next to a quaternary beta carbon. And that's quaternary because it has this carbon attached and then three others, 4 carbons total. It's a quaternary carbon, which is next to, so if you have a secondary carbocation next to a quaternary carbon, then you get an alkyl shift, which is actually the movement of one of these methyls to form a more stable carbocation. And this happens fairly quickly, and so it's just something you have to look out for. If you have a secondary carbocation, this is the other kind of shift that you can get when you get a, and remember these shifts only happen with carbocations, but if you have a secondary carbocation next to a tertiary carbon, then you get a hydride shift, which we won't show in this example because we don't have a secondary next to a tertiary, but that's just the movement of a hydrogen. It's the same idea, but let's show in the mechanism what this alkyl shift is going to be, because we have a secondary next to a quaternary beta carbon. What we actually do in the mechanism to show the movement of this alkyl, the alkyl shift, is we draw the line from the bond to the carbocation, showing that this whole group has moved over. So the product from this is going to be lead us to a whole new set of possible products. So now we've got the methyl group that shifted over. This is that methyl. I moved it down. We've still got a hydrogen we didn't show here. Remember, this carbon has a hydrogen and then the two other carbons attached to it. And now we've shifted where our carbocation is. We still have our two methyls that were there before. And now we have a carbocation right there. Now it's a tertiary versus a secondary, and that's more favorable. So this leads to a whole new set of products. Two to be specific, and so I'll show you how you can get those two products. One of the products you can get is if you use your water again as a base. The lone pairs on the water can take this beta hydrogen. Now this is a beta hydrogen because it's on a carbon that's beta next to the alpha carbon, the alpha carbocation. If this happens, those electrons fall in to form the double bond, and that will give us a completely new product with the molecules shifted around. Notice that's a double bond. I'll try to draw it a little bit more apparent there. And you can't get E or Z with this product because on this carbon you have two methyl groups, so there's no priority. So you don't get E or Z, but this is a distinct product of the reaction. Also, notice this is our new alpha carbon. We have hydrogens on both of these methyl groups. Okay? So another thing we can get after our alkyl shift. Remember, this is one of the most complicated examples that you can really go through because you're dealing with the shift of the alkyl, and it can kind of get a little confusing when you're trying to keep track of when you're going to get shifts. But this is the easiest way to remember it. Secondary next to quaternary, then you get an alkyl shift. Secondary next to tertiary, then you get a hydride shift. That means a hydride, the hydrogen and its electrons move over. But so now this is our carbocation still. Oh, let's draw that a little better. Carbocation. And these are new beta hydrogens, right? Because this is our alpha carbon and those are beta hydrogens. So another thing we can do is, sorry it's getting a little cramped here, but if we redraw our water and show it again being the base, pulling off one of these hydrogens and the electrons falling in to get rid of the carbocation, then we get another product, which is this. And you still have your methyl down there, and you get a double bond formed up there. So you have 1, 2, 3, 4 products from this reaction. Know that these two products you'll get from whether it goes by E1 or E2, because it can go by both because it's a secondary. Whether you do E1 or E2, you will get these products. But since we can get a carbocation, we also get these two products, which we wouldn't get if we did E2 because we don't have a carbocation with E2, and therefore we can't get a shift. So that's basically how you want to look at a really complex problem. First of all, can you form a carbocation, and if so, do you have a secondary carbocation that's next to a quaternary, you get an alkyl shift. And if you have a secondary next to a tertiary, then you shift a hydrogen on one of the beta carbons.